Today we're going to be looking at the derivatives of cosine, sine, e, and natural log. So the instantaneous rate of change of all those functions. Very first thing that we need to note here, and we'll go through and describe this a little bit more in detail in a second, but the derivative of sine is going to be cosine of x. Derivative of cosine is going to be negative sine of x. Tangent, we will worry about it later, but it is secant squared. We'll talk about that another time. So below here I have a sine graph. So this graph is y equals sine of x. And this is just kind of starting to prove and kind of start getting to think and feel about why is the derivative of sine of x represented by a cosine graph? So let's get some ordered pairs here and kind of talk about what this represents. We know that this is our first ordered pair, it's 0. 0, 0. And we also know that for this sine graph, the slope at this ordered pair, when we did that proof earlier, we know that the slope is going to be 1. And then we also know at pi over 2, my slope is going to be 0 because we're horizontal. We have a horizontal tangent line here. We are decreasing, so we have negative slopes from pi over 2 to 3 pi. And we know at pi, the slope is going to be about negative 1. At 3 pi over 2, our slope is 0. And then at 2 pi, our slope is 1. But we're increasing lots of positive slopes, right? All the way between 3 pi over 2 and 2 pi. So let's kind of take this information and start translating it to why does the cosine graph represent this? If I look, I see that my slope is 1 and that my slope is positive. So let's look and let's think for a second that our x values are still our x values, but our y values on the cosine graph here, or this cosine curve, let's say the y values are representing the slope. So your x is still going to be your input, and then your y would be the slope. So if I saw an ordered pair, let's call it right here. So if I saw an ordered pair and this ordered pair is 0, 1, what I'd be saying was at 0, the slope of the graph is 1. So let's take that and check back in. And when I look at that, I'm like, okay, at 0, the slope is 1. Well, guess what? On my sine curve, at 0, the slope is 1. At pi over 2, the slope is 0. So if I come over here and look at my cosine curve, the ordered pair at pi over 2 is 0. Additionally, we see that all the slopes should be positive between 0 and pi over 2, and my cosine curve is above the x-axis between 0 and pi over 2. Continuing on this trend, I notice that between pi over 2 and 3 pi over 2, right, we are going to have negative slopes with the highest negative slope of negative 1, and then we start decreasing at a decreasing rate. Again, we're negative. We go down to negative 1 at pi, and then we come back up to 0 at 3 pi over 2. Not coincidentally, as at 3 pi over 2, that ordered pair is 0. So at 3 pi over 2, that output is 0. So we're saying that slope at 3 pi over 2 would be 0. And then again, we're increasing, so we should be positive. We go through that 2 pi that has that slope of 1, and guess what? That ordered pair would be 2 pi 1. When I pull up my calculator, so my TI-84, I can do some checks here. So what I'm going to do is I'm going to go to my y equals, and let's get that all cleared out. When we go to math down to 8, that finds that derivative function. Remember, we're finding the derivative with respect to x, so that x goes in the denominator. We're derivating the function sine of x. And just so we see every value, if you just said x equals 2, it would only tell you the derivative at 2. So we want all the x values to be graphed, or the derivative of all the values. So right down here, I'm going to say x equals x, because that's going to give us all the unknowns, or all the derivatives of sine of x. When I look at graph, whew, that is really zoomed out. I'm going to go in here to a zoom 6, get that a little bit more zoomed in. We can zoom in a little bit more too, just so we're super clear on what's going on here. And guess what? It is a cosine curve. Wow, how wonderful. We could even go here and like, let's redo that and say, let's look at cosine of x, because we have an inkling, right? We said it's negative sign, but don't just ever believe things that are said, right? Always work them out and make it true for yourself. So when I go to that graph, and let's zoom out a little bit. When I go to that graph, I notice that it looks like a sine graph, but a sine graph that's been reflected over the x-axis. So again, the derivative of cosine is negative sine, right? Or a sine curve that's been reflected over the x-axis. When we are looking at this and like verifying algebraically, right? So we just looked at the graph and we evaluated the slopes and went kind of back and forth there. But when I'm actually thinking about like, okay, let's algebraically prove this, that the derivative of sine of x is cosine of x. I want us to recall, and we talked about this and we looked at this using squeeze theorem, that when you have the limit as h approaches 0 of sine of h over h, that value is 1. For cosine of h minus 1 over h, that value is 0. Additionally, pulling from some of that knowledge in pre-calculus, you guys also talked about how do we expand cosine of x plus h and how do we expand sine of x plus h. So when we fully expand cosine of x plus h, you should get cosine of x, cosine of h. So we have cosine of x, cosine of h, plus sine of x, sine of h. And then with that sine of x plus h, you would have had sine of x, cosine of h, plus cosine of x, sine of h. And these are just some identities that we pulled from some prior knowledge here. So we're going to use those to actually get some really intense math going on here as a proof. And guys, I totally messed up here. This should be a minus. It's been a while since I've done this. All right, let's get this going. Let's show that the derivative of sine of x equals cosine of x. I'm only going to do it for sine, and if you really, really want and have just so much free time and are so bored, then you can prove that sine limit later. So the derivative of sine of x equals cosine of x. Let's rewrite that as the limit. So I'm going to say dy over dx sine of x equals the limit as h approaches 0 of, and I'm going to write that format in. Remember, we are going to have sine of x plus h minus sine of x all over h. Now I'm going to use that identity because I said already sine of x plus h is equivalent to sine of x cosine of h plus cosine x sine of h, and I'm just going to substitute for that piece of my equation. So let's keep that on writing. Make sure that is not going to be a naked limit, right? We're always filling that in. And I'm just going to substitute sine of x cosine of h plus cosine x sine of h minus sine of x all over h. I'm going to pull some of this together because our whole goal, right, is to get some stuff to cancel out, to get some substitutions occurring here. So I'm actually going to go in and factor out a sine of x because I know that I have two terms that have a sine of x. I don't have two other terms in any of these others, so I'm just going to combine this term negative sine of x and sine of x cosine of h and write that as sine of x times cosine of h minus 1, and then we still have plus cosine x sine h all over h. So I also know that when I'm looking at this guy right here, this h is the denominator for both of these terms, correct? We're just like writing them all combined in the numerator. I also know that according to my evaluations earlier, that sine of h over h is going to be 1. I also know that cosine of h minus 1 over h is 0. So I see that that's occurring here, right? We have that cosine of h over h. So that means that that is 0, and I can cancel that out. So we can just cancel that guy out. So let's get that written here. we're going to have, this is the limit as h approaches 0. This is going to cancel out. We are left with, this all cancels out, right? So we're left with the limit as h approaches 0. We're left with cosine of x, sine of h, all over h. And we also know that this simplifies down to 1. So with a little bit of some fancy canceling, I get that this is going to be cosine of x. I'm going to give it a pause here if you guys want to try sine of x on your own, and then I'm just going to throw in that answer so you can check your work. All right, there is that work and that proof all here if you took time to pause and get that done. So all in all, our summary is that the derivative of sine of x, or f prime of sine of x, is cosine of x. And then the derivative of cosine of x, f prime of cosine, is going to be negative sine of x. Let's get into our last little section here, just looking at derivatives of logarithmic and exponential functions. There are two really kind of funky things that happen here with exponents. So e to the x is the only function that has the derivative of itself. And the reason why is, like, think about trying to apply that power rule here. If you think of like e raised to the power of x, that's that like exponential growth or exponential decay, right? Depending on like what my base is. But if I'm thinking about what's happening here, if I swung that x down in the front and then subtracted by 1, like that doesn't really do anything to the degree. We could also do a whole lot more proofs, look at a lot more graphs, but e to the x always has e to the x as its derivative. The derivative of natural log of x is going to be 1 over x as long as x is greater than 0. And that was a mouthful there, so let's actually kind of look at the graph. Remember, we always want to ground it based on what we know. You know that a natural log curve follows like a logarithmic curve. And so when I'm thinking about what's going on here, we know that we're going to have very, very high slopes, right? Because that approaches 0. That slope is almost straight up and down. And then that slope gets a little bit more level, and then it gets very, very tiny. So just like we did when we looked at that sine curve, let's think about what that 1 over x graph looks like. Remember, we're only using x is greater than 0, so we're not going to be using that left-hand side of the graph. We're just looking at this right-hand side of this rational function. If this represented the slope, so let's say that this is e to the, this is 1 over x, and this represents slope of the natural log. Let's look at that. So we're saying like at 1 or at really tiny numbers, my value or my output is very, very high, and we said that, right? Our slope is super, super high the closer we get to 0. And then we start flattening out. We have almost like some very normal numbers, and then we get closer and closer to 0, or like a very, very low slope. And that's what we see here. Our slopes get closer and closer to 0, never completely 0, right? Because there's an asymptote there on that 1 over x. And this graph here is never going to completely flatten out, but it gets very, very close to doing so. So what does this look like? Let's get it done. We're also going to use some log properties because I see the natural log of x cubed, and I'm like, what does that do? Is that like 1 over x cubed? And no, it's not. Move that 3 to be a coefficient, and let's rewrite that as 3 natural log of x. I know that the natural log derivative is 1 over x, so this just becomes f prime of x equals 3 times 1 over x, which is going to be 3 over x. When I have the natural log of x squared times e to the x, fun stuff happening here. I'm going to use my logarithmic properties to expand. So I know that multiplying two things by logs, I can rewrite that as the natural log of x squared plus the natural log of e to the x. Again, let's get rid of my exponents by creating coefficients. So my original function, g of x, is equivalent to the natural log, I keep on wanting to put an I there, I don't know why, of x plus x natural log of e. When we derivate, g prime of x equals, all this first term becomes, it's going to be 2 over x, right, because you have 2 times 1 over x. And then the natural log of e is 1. And then the derivative of x is 1. So it's just going to be 2 over x plus 1. Or that slope, right, is just positive 1. We have the natural log of x minus 1 over x. So again, guys, we're always wanting to rewrite with everything in the numerator. So I'm going to rewrite this as natural log of x minus x to the negative 1. So then when I derivate here, you just have 1 over x. And then that negative 1 times negative 1 is a positive 1. X to the negative 2. Rewrite to rationalize that exponent. And we get 1 over x plus 1 over x squared. Box it and you are done. Again on D, when I'm looking at something like D, we're using those logarithmic properties, and I'm just gonna do all of this at once. I'm gonna say that this is going to be 2, we need to expand that a little bit more, huh? There's a lot going on here. So this is gonna be the natural log of 2 plus, right, because there's 2 terms being multiplied in that numerator, x natural log of e, and then we have minus the natural log of 3, and we also have a minus the natural log of x. This would be, oh, sorry, that would be a plus right there because those are being multiplied. And that negative gets distributed and then it turns into a minus. My brain was just working a little bit faster than my pen was. So that negative gets distributed. We have minus the natural log of 3 minus the natural log of x, and we can get rid of those parentheses. Now when we derivate, we're thinking about like, okay, let's get this done here. You know that the natural log of 2 is a value. Don't get confused because ln are letters. That's not a variable. That's just going to be a straight value. The natural log of 2, the derivative is 0. Natural log of e cancels. The derivative of x is just going to be a plus 1. Natural log of 3, again, it is a constant, so the derivative of that is 0. And then we also have the natural log of x, so we're just going to derivate with our natural log rules, and that's going to just be minus 1 over x. So all in all, we get that y prime is going to be 1 minus 1 over x. Just 2 more examples and we're done. Let's look at this. We have the natural log of 4x cubed e to the x. Again, I'm going to fully expand this. I'm not derivating yet. I know that this is the same as the natural log of 4 plus 3 natural log of x, right? I took that exponent and made it a coefficient. And then we also have a plus the natural log of e to the x. X natural log of e. There we go. Taking that exponent out of the picture. Again, when you're derivating the natural log of a constant, you guys know this, is 0. We have plus 3 over x. Natural log and e cancel, so then we just have plus 1 over x. So f prime of x equals 3 over x plus 1 over x. Last but not least, let's get this guy done. We have g of x equals, let's rewrite, pi e to the x minus, I'm going to make that exponent negative 2/3, right? Because remember that root index becomes the denominator. And then also, since I pulled that up to the numerator, that fraction becomes negative. When I derivate here, we run into our first really fun situation. The derivative of e to the x is just going to be e to the x. And then this next guy, that negative 2/3 gets multiplied, so we have a positive 2/3. And then remember, we're subtracting, so we're saying what's minus 3 over 3 for that negative 2/3. And then we get that's a negative 5 over 3. So we have x to the negative 5/3. When I rationalize that exponent, I get pi e to the x plus 2 over 3x to the 5/3. And you are done. Guys, I will see you on Monday, and we'll talk about this more.